do you do to solve for it? So we could subtract. Don't write anything down. Alright, so, but it's not, I mean, it's like you gotta try something. So if you take it to the other side, now I have a cosine minus the sine plus 1. You can't really pull out a GCF, but there's not a GCF. They're not squared, so I can't say, oh, this magically becomes sine squared plus cosine squared equals 1. So we can't use that identity. So that might not be something that we would want to do, but it's a try. It's like a thought. Emma, you had your hand up. She's like, never mind. So let's go back. Gotta try something else. So think of equations that we have solved and different methods that we have used to solve them. Besides factoring or getting everything on one side. What else have we done to like various equations to try and solve them? And I know you solved, I don't know, 10 different functions over the last 2 years. Dylan?
Multiply by the conjugate.
We could multiply by the conjugate. We could definitely multiply by the conjugate on both sides. That could be something. And Dylan, you are so close. We're not going to divide by the conjugate. If you have an equation that said the square root of x minus 2 equals x plus 6, what would you do here? Square both sides because you want to get rid of the square root thing, right? So, I said Dylan was close. Squaring both sides is a method that you can use to solve equations. So, we're going to try that method for here, which is similar to the conjugate. When you square both sides and there's a quantity, you have to square the quantity grouped together. I can't just individually square terms. So, if there's a pair, a group, a quantity, both of those need to be squared together. Just like over here, this x plus 3, that quantity would be squared together. We're also going to square the other side. So when you square cosine plus 1, that quantity, what does it mean that you're doing with squaring that, Colin? Right. So you're foiling that. What do you get when you foil that?
Cosine squared x plus 2 cosine x plus 1.
And on the other side, you have sine squared. Okay. So how does that help you?
Because sine squared x is cosine squared minus.
Yeah. Because now on the other side you have a sine squared x. And we can change that. If I have all cosines on the left side, you're probably going to get all cosines in the equation. So we don't really work with multiple functions if we don't have to. And now that the sine is squared, we can change that to be 1 minus the cosine squared. That's where those identities come in. So we squared both sides. It's a method you can use to solve equations. You can do anything you want to an equation. We could have used a conjugate. Conjugate just wouldn't help us with the right side trying to get rid of that sine so that we have all the same function. So on the other side then we have the cosine squared, 2 cosine, and then plus 1. So at this point, if we go back to Colin's original thought, now we want to take everything to one side because they're all cosines. So if we set it equal to 0, we would subtract a 1 and add the cosine squared. So we do, what, 2 cosine squared plus 2 cosine. And nicely, the 1's cancel. So when those 1's cancel, we don't have to use AC grouping. The 1's are gone. That extra number is gone. So Carrie, what would you do instead to solve this?
Factor out the 2 cosine.
Yeah. And when you pull that out, what do you have left inside?
Cosine plus 1.
So zero product property, it's now factored. You have 2 products. You take those products and set them equal to 0. So 2 cosine equals 0, which really means, Carrie, the cosine is equal to.
0,
And then the other one, cosine would be equal to
-1.
-1. So zero product property. The first one is equal to 0, the parentheses is equal to 0, and then you find the angles. So we're not done solving because really our goal is to find x, and in our case, x would be the angles. Carrie, if we're talking about cosine, when is the cosine 0?
0 and 5. Or 0 and just 0. And 2 pi. Right?
When's the cosine 0? When is x 0?
Pi over 2 and then 3 pi over 2.
There you go. So pi over 2 and 3 pi over 2. Carrie, when is cosine -1?
Pi.
Or pi. There we go. Okay. So questions so far? So we squared both sides to enable us to use an identity, just like we use conjugates to enable us to use an identity. Squaring both sides is a process for solving equations that we can do. Except, going back to this problem here, when you squared both sides, we would have ended up with x minus 2, x squared, 6x plus 9. And then we'd set it equal to 0 and factor. Does anybody remember what you did when you had these types of equations after you got your two answers? You check them. Do you know why we check them?
Because if you got a negative or something in the radical, it wouldn't work.
Right. When you manipulate an equation, so you're taking an equation and you're adding extra powers to it. We initially just had an x. We squared it, we got x squared. So you're adding exponents, you're adding x's, you're adding solutions. And when you do that, and unfortunately you have to because that's the only way you can solve. But when you do that, you end up getting extraneous solutions because you added extra values, extra x's. You manipulated the original equation. We have to check to see which one of these angles work. Now, there are 3 of them, so all 3 could work. 2 of them could work. 1 of the 3 could work. When you check it, go back to the original. And it isn't a hard check. It's not too bad. But we're going to plug in the angle of pi into the original problem. So we have the cosine of pi over 2 plus 1 equals the sine of pi over 2. So I'm just kind of showing you how this works. When you check something, you're now plugging an angle in. What is the cosine of pi over 2? Up here. 0. What is the sine of pi over 2? 1. Does 1 equal 1? Yes. Okay, so we know that pi over 2 is good. I'm going to put a box around that. If I check the next one, we have 3 pi over 2. What's the cosine of 3 pi over 2? Right here. 0, because I already found the cosine of 0 was 3 pi over 2. What's the sine of 3 pi over 2? Minus 1. Does 1 equal -1? Nope. So cross that guy off. And then do one more time, plug in pi. So cosine pi, sine pi. So the cosine of pi is already your answer. That was -1. -1 plus 1. The sine of pi is 0. Does -1 plus 1 equal 0? Yes. That's also a solution. So I got one extraneous solution. And that was the angle of 3 pi. It's a long problem. Anytime you square both sides, you're going to have to check your solution. If you don't use that process, then you don't have to check your solution. I mean, you can so that you know it's right, but it's just when you're manipulating and adding extra things to the equation. Questions? problem switches gears just a little bit. And the equation is actually a lot shorter. It says 2 cosine, but instead of just having an x there, or a y, or a theta, there's a number with it. So we have 2 times the cosine of 3t, and then it's equal to 1. So if we use what we did yesterday, Josh, what would you do to isolate the cosine? Yeah, we're going to do that same thing, divide by 2. And then Josh, based off of what we did yesterday, what do you do next? What do you think next?
Probably next you're gonna find the cosine.
Yeah, now we find the cosine of 1/2. It's not changing. We're still going to find the cosine of 1/2.
I know what to do.
Oh, good. Where is the cosine 1/2?
The cosine of 1/2. 2 places. One of them is pi over 3.
Awesome.
The other one is 5 pi over 3.
Perfect. Good. All right, so same as yesterday. Nothing has changed.
Yeah.
Yes. Except that now I have a 3t here, or a 3x. So we're going to take that 3t and place it equal to pi over 3. We're going to take the 3t and place it equal to 5 pi over 3. I need you to go back in your mind and think about graphing. Oh. Does anybody remember what that 3 does to the period? It makes it smaller. What is a typical period of sine or cosine? 2 pi. That number is b, and it makes our 2 pi smaller. So it cuts it in thirds. So in theory, I now have 3 periods. That's what that number means. 3 periods from 0 to 2 pi. So how many angles do you think you would have then to correlate with the fact that we have 3 periods from 0 to 2 pi? 3. Not 5, but 3. So we need to calculate all of the angles. This number here gives me multiple angle solutions because it's taking the typical period and shrinking it into thirds. So now I have 3 graphs, which means each one of those graphs has an angle that corresponds with it. So to help us get that angle, we're going to add 2 pi to this so that we can then have a value to continue to calculate other angles. And I'm going to add 2 pi. So we're actually kind of finding like a general form. And the reason we're going to do this is so that we can get that new period, which I already have over there is 2 pi over 3. So if I need to get the t by itself, Colin, you were saying you would divide by 3 or multiply by a third. So Colin, that changes this first number to be then pi over 9. And then my period is 2 pi over 3. So the angle is actually not pi over 3, but it's going to be pi over 9. That's one answer. I need 3 of them. So how can I get a common denominator so that we can continue to find another one? So if we multiply this by 3, it becomes 6 pi over 9. So if I take pi over 9 and add 6 pi over 9, I now have 7 pi over 9. I need to do that one more time because the 3 means there are now 3 periods in one cycle from 0 to 2 pi. So if I take 7 pi over 9 and add 6 pi over 9, I get 13 pi over 9. So now I have 3 angles where typically we only have 1. And that's because of the 3 in front of the t. That tells us we have multiple periods from 0 to 2 pi. Josh?
So what did you do with the 5 pi?
We didn't do anything with that yet.
Oh, okay.
Yep.
My bad. We're gonna have more.
We're gonna have more answers. So Josh
Yes.
just said this becomes 5 pi over 9. and 2 pi over 3, which is really, again, 6 pi over 9. So Josh, what would my next pair of angles, or group of angles, not pair?
So you have 5 pi over 9, then you'd have 11 pi over 9. So you add another 6.
Add another 6 to this one.
17.
There you go, 17 pi over 9.
Solutions.
So for each angle, each answer, you have extra values. Whatever the number is in front tells you how many extra angles you're going to have for that pair, for that set. So we use pi over 3 from the original that Josh gave us. We used that to find the answer, but we had to then apply this part right here. It's called a multiple angle. So I now have multiple periods from 0 to 2 pi, because Hannah said the period shrunk. So now my graph is a third of what it initially was.
Will there ever be a fraction from
Yes, the next one we're going to do has a fraction. So what does a fraction usually do then, Hannah? It makes it bigger. So that means you would have less answers, because now the period is bigger than 2 pi instead of smaller than 2 pi. So those are actually nice because you have less instead of more.
Do we have to check?
No, you don't have to check these. Phew. The only time you have to check is when you square both sides.
Okay, there you
Woo.
go. That was like vertical.
No, not with the multiple angle. All right, so let's see if we can look at the next one to answer Hannah's question. Will you ever have fractions? Yes. So this one says solve the equation. These equations are usually easier to solve because the answers might require a little bit extra work to get there. The angles. So we have 3 tangent x over 2. Take the 3 to the other side. Divide by 3. Hannah, you end up with the tangent of x over 2 equaling negative 1. So you don't do anything with the x over 2. You still approach the problem the same way. 3 squares tangent negative. Two and 4. That's right. All right, so tangent is sine over cosine or y over x. How would you get a negative 1 from their ordered pairs in the unit circle column?
Would it have to be the negatives? Yeah, negative square root 2 over 2 and square root 2.
Right. That would have to be our ordered pair. To get a 1, x and y need to be the same. The only time they're the same is the square root of 2 over 2, square root of 2 over 2. What angle, like family, does that go with? Pi over 4. So that's the family we need to think about, pi over 4. But Reese said it should be in the second quadrant and the fourth quadrant. So that means it's going to be 3 pi over 4 and 7 pi over 4. So those would be the initial angles, the initial answers. Okay, so the next step. Those would be my answers if it just said x, but this one says, yeah, a half x. Or x over 2. When it's tangent, what's the period of tangent? Pi. So Emma, if we take this, if it's x over 2, how do you solve for that? You multiply it by 2. So times 2. All of this is doubled times 2. So Emma, 3/4 times 2 becomes, and pi times 2 is 2 pi. So what would a specific angle be? What's the first angle answer? This right here, 3 pi over 2. That's my first answer. If you add 2 pi to that, what is 3 pi over 2 plus 2 pi? 7 pi over 2? How big are the angles supposed to be? Between 0 and 2 pi. So if I already have 3 pi over 2, which is down here, 2 pi to that, your answer is going to be bigger than necessary. So you have 1 angle answer instead of having 2. You half the amount. Usually we have 2, but because there's a half in front of it, the period is actually bigger because it's double. So then my answer is I would have less answers because the period is longer than 2 pi. So let's talk about the other one underneath. Carrie, what happens when you multiply this one by 2?
You get 7 pi over 2 plus 2 pi.
What's wrong with 7 pi over 2?
It's already bigger than
Yeah.
2 pi.
It's already bigger than 2 pi. That one's too big. So how many answers do you have?
One.
1. Only 1. Those are harder. Like algebraically, it's not. It's easy. But thinking about it is a lot harder. Because it's not just the answer. We have to make sure we're kind of doing something with that angle. So if you have a fraction, you should have less answers. If you have a whole number, that whole number tells you how many answers you should have. 4 or 3 or 2 questions. So there is one more problem that we are going to at least try and start. So we're going to switch gears one more time. So we had 2 problems where like we were manipulating the angle, and now we're going to go back into a problem that was similar to the first one. Find the general solutions. It should say from 0 to 2. Oh no, it says general, so we don't need 0 to 2 pi. But we have secant squared minus 2 tangent equals 4. No, you don't have to square both sides.
So would you substitute the secant squared for tangent squared?
Yeah, but instead, if I have a secant squared, we don't have to square both sides since you already have something squared, but we need to make sure the functions are the same. So if you have a tangent already in the problem, and we know 1 plus tangent squared equals secant squared, we can take out the secant squared and replace it with 1 plus the tangent squared. That way we have the same function throughout the problem. I'm also going to just take the 4 to the other side and set it equal to 0. So we didn't have to square both sides because the thing was already squared. The secant was already squared. So we can just replace it with its identity. And then combining some like terms, we end up having tangent squared minus 2 tangent squared, or minus 2 tangent, sorry, and then minus 3. Brenton, how would you factor it? What 2 numbers multiply to be negative 3 that combine to be negative 2? Negative 3, 1. And then the tangent is positive 3, and the tangent is negative 1. We just said this answer from above. When was the tangent negative 1 from above? 3 pi over 4, and Josh, you gave these to me, right? No. Who gave these to me? 7 pi over 4? Is the tangent ever 3 on the unit circle? No, but the tangent can be 3. It just isn't a number that's on the unit circle. So is that going to give you an exact answer? No. So the way you get the angle by itself, how do you get the angle by itself? Ooh, Carrie, say it again. Inverse tangent. Now, would you have to use a calculator to get that answer? Yes. Do I want you to use a calculator to get the answer? No, actually I don't. Just leave it like that. No. Oh, look, we got it. So tonight's homework is going to be like requiring some identity. Put Pythagorean identity. You might have to square both sides. Anybody interested in trying 49 or 62? Emma and Hannah? Emma, 49. Hannah, do you want to try 62? I think it's one of those multiple angle ones.